Good afternoon, grade 12s. Welcome to our Matric revision program for this afternoon. We're now going to focus on probability, and in particular, the grade 12 concept of the fundamental counting principle. If you notice on the monitor that probability is about 15 marks in mathematics paper 1. And in our revision booklet for term 3, from pages 8 to page 15, you'll find a very good summary of different questions that revolve around probability. Now, please note that all the probability content from grades 10 through to 12 will be assessed in the grade 12 final examination. Moving on, we are going to do a quick preview of, and revision, of course, of the various concepts that you have learned over the years. Firstly, you may recognize the probability formula. Probability formula says the probability of an event occurring, that's the P of E, is equal to the number of times that event occurs divided by the number of times in the sample space, or the total. Next, you had the addition rule of probability, and we have an entire telematics broadcast that dealt with this as well. P of A or B is equal to the P of A plus the P of B minus the P of A and B. You may remember one of the ways we remember this is the rhyme or is equal to A plus B minus and. So please have a look at that telematics broadcast that dealt with the addition rule of probability. Moving on, mutually exclusive events. For mutually exclusive events, the probability of A or B is equal to the probability of A plus the probability of B. This means that the probability of A and B in that addition rule is equal to 0. And then for complementary events, we also learned that the probability of A plus the probability of B is equal to 1, and we did calculations in that connection. Then for independent events, we handle the product rule. Here, the probability of A and B is equal to the probability of A multiplied by the probability of B. Now, the following 3 probability arrangements that were done in grade 11 will be examined in the grade 12 final examination. Venn diagrams, tree diagrams, and two-way contingency tables. And we can throw in probability questions attached to those arrangements as well. Now, we come to this grade 12 concept, the fundamental counting principle. The fundamental counting principle states, suppose there are n ways to make a choice, and for each of these there are m ways to make a second choice. Then the number of possible outcomes will equal m multiplied by n ways. Now, that's a lot of words. Let's look at this as an example. Well, if n items, as you can see on the monitor, can be arranged in a row, then this can be done in n factorial ways. Notice, this is where no repetitions occur. So this sign here that looks like an exclamation mark is what we call in mathematics factorial notation. Now, on the calculator, you may notice that this is a function that's given there. If you have your Casio calculator, the way to encode factorial notation is you press Shift and you press this particular button here, and there you have your factorial notation. So if we look at that, factorial notation means, as you can see from the monitor, 5 multiplied by 4, multiplied by 3, multiplied by 2, multiplied by 1. Now, you know, certain numbers, we can say 11 multiplied by 10, multiplied by 9, and we can go on and on and on. Why go that long route? Let's make life easy and let's make life beautiful, because that's the way it is. We use factorial notation. So if we have to look for 5 factorial on the calculator, what we do now is we say 5, and then we press Shift and this factorial notation, and there we have our answer. As the calculator shows, this answer is none other than 120. And if you notice on the monitor that 5 factorial is 120 ways. That's the number of ways that that can be arranged. Let's go to how these questions look in exam papers. From the November 2014 DBE paper 1, question 12 had the following situation. A password consists of 5 different letters of the English alphabet. Now, grade 12s, we need to recognize that in the English alphabet, we have 26 letters, right? Also, we need to know that the alphabet is made up of vowels There are 5 of them. And the balance we call consonants. Right? You got that? So we have 5 vowels, A, E, I, O, U. And we have 21 consonants. These are non-vowels, one can say. Right? So keep that in mind. Then we move on. Each letter may only be used once. Notice, password has 5 different letters. How many passwords can be formed if all the letters of the alphabet can be used? Right? They can only be used once. So a very easy way to do this is just to draw 5 spaces. Right? So there's 1, 2, 3, 4, and 5. Now, let's have a look. There are 26 letters in the alphabet, so all 26 qualify for the first space. One of them is used up for that one, so I can't use it again. I'm left with 25. 2 of them are now used up. I can't use them, so then I'm left with 24. 3 of them are now used up, and here I'm left with 23. And the 5th is 22 are left. And all I do now is I simply multiply these and get the answer to my question. When I multiply that, as you can see on the monitor, 26 multiplied by 25, multiplied by 24, multiplied by 23, multiplied by 22 will give me the amount of 7,893,600 different ways. Moving on, the password must start with a D and end with an L. So if we look at our paper down here again, it must start with a D and it must end with an L. Remember, the password has 5 spaces. So I'm left with 3 now, and I must find out exactly what goes there. Well, there we have it. It must start with D and it must end with an L. So I've got 3 spaces to fill. So of the 26 letters in the alphabet, I've used 2 already. So how many qualify to be used first? I can hear you saying it. You're right. 24. Right, so now there's 1, 2, 3. I must take the 3 away from 26. I'm left with 23. And the same is true of that one, 22. When I multiply these here, notice on the monitor, there I have my answer. 12,144 ways or letters can be used. Here's another question. 7 cars of different manufacturers, of which 3 are silver, are to be parked in a straight line. In how many different ways can all these cars be parked? Well, simple solution. 7 multiplied by 6, multiplied by 5, multiplied by 4, multiplied by 3, multiplied by 2, multiplied by 1. And I can actually hear you saying it. That is grade 12, simply 7 factorial number of ways. And there's the answer, 5,040. Well done. Moving on. If 3 silver cars must be parked next to each other, determine in how many different ways the cars can be parked. Well, the 5 units can be parked in 5 times 4 times 3 times 2 times 1 ways. In other words, 5 factorial ways. The 3 silver cars can be parked in 3 factorial ways, which is 3 times 2 times 1. So when we combine 5 factorial multiplied by 3 factorial, we get an answer of 720 ways to park these cars. Look at this question, which was drawn from the November 2015 DBE paper. It said, the letters of the word decimal are randomly arranged into a new word, also consisting of 7 letters. How many different arrangements are possible if, number 1, the letters may be repeated? Next, the letters may not be repeated. Then, the arrangements must start with a vowel and end in a consonant, and no repetition of letters is allowed. Let's have a look at that one. The letters may be repeated. Notice the word decimal has 1, 2, 3, 4, 5, 6, 7, right? So there are 7 spaces, right? We just have to do it on this paper here. 1, 2, 3, 4, 5, 6, and 7. Right. Now, they can be repeated. For the first place, simply 7. Right? There we go. For the second place, 7. Next one, 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 7. We multiply all of these. There we have our answer. And as we notice, there the answer is given to us, That is simply 7 to the power 7. The calculator will tell us that it's 823,543 ways. Going back to question 11.2, when the letters may not be repeated. Now we have a different situation. We still have our 7 spaces, and we are going to find out how we can use this. 1, 2, 3, 4, 5, 6, and there we have 7. Now the question says they cannot be repeated. So we know 7 qualify for the first one. That 1 is used up, therefore 6. Therefore 5, 4, 3, 2, 1. And when we multiply these, you may recognize this particular format can be simply written as 7 factorial. Take your calculator. Let's find the value of 7 factorial. 7 factorial. Calculator is going to give us the answer. Can you see the answer? 5,040 ways. There we have it. Now, question 11.2.3 says the arrangements must start with the vowel and end in a consonant, right? And no repetition of letters is allowed. Well, that's quite easy. There are 3 vowels and therefore 3 options for the first position. There are 4 consonants and therefore 4 options for the last position. Where do we get 3 and where do we get 3 vowels and 4 consonants from? You may be saying, well, look at the word decimal again. The vowels are E, I, and A. Not so? So there's 3 of them. What about the consonants? The consonants are D, C, M, and L. So this word has got 3 vowels and 4 consonants. Looking back to the solution now, the remaining 5 letters can be arranged in 5 factorial ways. However, what we must do here now is we must have 3 multiplied by 5 factorial multiplied by the 4, and we get our answer of 1,440. Very easy. Now, the fundamental counting principle doesn't just stop at calculating things using factorial notation. Probability is brought in and is included in calculations involving the fundamental counting principle. Let's look at an example of this from a past examination paper. Here from the June 2016 DBE paper, question 11 said, 5 boys and 4 girls go to the movies. They are all seated next to each other in the same row. Notice what question 11.1 says. 1 boy and a girl are a couple, right? And they want to sit next to each other at any end of the row. And of course, we recognize that the row has got 2 sides to it, okay? In how many different ways can the entire group be seated, right? Notice that question again. 1 boy and 1 girl are a couple, and they want to sit next to each other, right? So we need to remember that the boy and the girl represent 2 factorial. In other words, either the boy can sit first and the girl after him, or the girl can sit first followed by the boy. That's why we say 2 factorial. So there we have 7 factorial that will follow there, right? Because from the 2 plus the 7 we get 9. 5 plus 4 is 9, right? And so we put that there. Multiply that by 7 factorial, that's the balance. But because there are 2 sides in the row, we say 2, not 2 factorial, but 2. When we multiply that out, we get 20,160 ways. That's the number of ways that they can be arranged based on what we are given there. Question 11.2 involves the probability. If all the friends are seated randomly, calculate the probability that all the girls are seated next to each other. Well, what does the solution look like? If all of them are seated, we have 9 factorial ways. Remember, they are 5 and 4. That means 9 factorial on the calculator is 362,880 ways. When the girls are seated together, there are 4 factorial ways. With the girls taken as one unit, they will be seated in 4 factorial multiplied by 6 factorial ways. And there we get 17,280. Now the question said, calculate the probability, right? So the probability, using the probability formula, remember P of E is equal to the N of E divided by the N of S, right? We have the probability that all the girls are seated together will be 4 factorial multiplied by 6 factorial divided by 9 factorial. If we have to expand that on the calculator, in terms of numbers, we're looking at 17,280 divided by 362,880. That is our sample space. When we simplify that, we get 1 over 21. Now, you may remember from previous broadcasts, as well as your teacher probably told you, the answer to any probability sum can be given as a fraction, or as a decimal, or as a percentage. And we've given you all 3 in this case. You just need to use one of the 3. Here, the answers that we will honor will be 1 over 21. You can express that as 0,047619. That's as a decimal. And finally, as a percentage, when you multiply that by 100, you get 4,76%. Very easy question. Look at this one, drawn from the DBE June 2018 paper. Question 10. Ben, Nhlanhla, Owen, and Derek, and 6 other athletes take part in a 100-meter race. Each athlete will be allocated a lane in which to run. The athletics track has 10 lanes. Question 10.1. How many different ways can all the athletes be allocated in a lane? Well, that's simple. It's simply 10 factorial. The calculator tells us this is 3,628,800 different ways. The next part of the question. 4 athletes taking part in an event insist on being placed in lanes next to each other. In how many different ways can the lanes be allocated to the athletes now? Well, there we have our 4 factorial, indicating those 4 athletes that want to be next to each other. And the balance would amount to 7 factorial. When we multiply these two and find the product, we get 120,960 different ways that can be done. And then question 10.3. If the lanes are randomly allocated to the athletes, determine the probability. We're going to use the probability formula here now, that Ben will be placed in lane 1, Nhlanhla in lane 3, Owen in lane 5, and Derek in lane 7. Well, that amounts to the fraction 6 factorial divided by the sample space, you may recall, which is 10 factorial. When we simplify that, we're going to get 1 over 5,040, that's our fraction, or we can express that as a decimal if you want to, and there we have that right there. Okay? So very interesting calculation from there. Grade 12s, once again, to master the fundamental counting principle as well as probability. Practice, practice, practice. Remember the motto, plan your work, then work your plan. If you follow those guidelines, you will do very, very well in your mathematics. And we wish you well as you prepare for your final examination that is coming up very, very soon. In our next segment of our Term 3 revision, the final part, we're going to focus on trigonometry. We know that gives many learners nightmares in paper 2, but don't worry, you will do very, very well. So keep practicing, keep working out past question papers, working through study guides, and in everything you do, plan your work, then work your plan. Bye-bye.